In this video, I would like to say a few words about my new work published in New Journal of Physics. We address two main questions. Is it possible to accelerate vortex electrons with orbital angular momentum to ultra-relativistic energies of at least several MeV or even GeV? And the second question is it possible to generate quantum vortex states of particles heavier than electron, namely protons, antiprotons, ions, and so on? We give positive answers to both the questions. To prove that, we need to adapt the ideas and methods of the classical beams in accelerators to quantum physics of wave packets. During the last 20 years or so, a new method has been developed in accelerator physics community to generate round beams with unquantized angular momentum, the so-called angular momentum dominated beams. The main idea is to immerse a cathode into a field of a solenoid. The electrons emitted from this magnetized cathode carry canonical angular momentum, which is converted to the kinetic angular momentum when the beam leaves the solenoid. This method has been experimentally realized, for instance, at Fermilab in USA. A somewhat similar thing happens with the quantum state of each electron. The canonical angular momentum is converted into a quantized orbital angular momentum of the electron packet when the particle leaves the field. This represents a new way to generate quantum vortex states. In accelerator physics, there exists a so-called Busch theorem which connects the unquantized angular momentum of the classical beam, the solenoid field strength, and the beam width in the solenoid. We give a quantum generalization of this theorem, which shows how the quantized angular momentum of the wave packet is connected to the field strength to the transverse coherence length of this packet. The angular momentum is due to a quantized flux of the magnetic field through an area of the wave packet itself. The ion or proton beams, in their turn, with unquantized angular momentum, have been already generated in a similar way when one employs a magnetized stripping foil immersed into a solenoid to change the charge of the particles. It turns out that the quantum state of an ion or a proton can also turn into a vortex state as a result of such a stripping in the solenoid field. Importantly, both the unquantized angular momentum of electron or ion beams and the quantized angular momentum of single particles are conserved in linear, that is, weakly inhomogeneous, fields of electric and magnetic lenses employed in accelerators and electron microscopes for focusing and phase space manipulations. Thus, our work demonstrates that, on the one hand, new ideas for quantum optics and particle physics can also be borrowed from the classical world of accelerators and beams. On the other hand, experimental realization of these ideas can open a new vista for the field of vortex states and to make them a new tool in atomic and molecular physics, in high-energy and hadron physics, in heavy ion physics.